This is the review video for acids and bases, and we'll get right into it. There's a couple of things that are kind of, grade 10, basically easy stuff. Acids taste sour, they turn litmus paper red, they neutralize basic solutions. Bases taste bitter, turn litmus paper blue, and feel soapy or slippery. So yeah, that's quickly done. We're not going to spend too much time with the Arrhenius definition because it's old and outdated and we don't really use it anymore. But what this says is acids in water produce H plus ions and bases in water produce OH minus ions. So what that Arrhenius basically said, if the chemical formula of something had a free H in it followed by something else, this would be an acid. And if the chemical formula had something plus an OH minus ion, this would be a base once you put it in water. So that was his definition. And obviously there are the limitations here, which are important to know what the limitations of this theory are, is that H plus does not exist alone in water. It automatically forms H3O plus, even though we commonly do write H plus sometimes, but we mean always H3O plus because it exists at least when we're talking about an aqueous solution. Ammonia is basic, even though it does not contain OH minus, but the pH of ammonia is above 7, so we can't explain. Arrhenius couldn't explain that. And then it only works for aqueous solutions. So this was for example, HCl gas would not have been considered an acid, even though it is. So here we learn about the Bronsted-Lowry theory, and this is the basis of what a Bronsted-Lowry theory is. So again, we'll just review that a hydrogen atom originally had one proton and one electron that's roaming around in its first shell. And then if we then remove this electron, this becomes the ion H plus, which just means a proton, right? So normally when we say protons, we mean H plus ions. Those are the same thing. So here, acids are donating H plus and bases accept H plus. What does that mean? So essentially it's the same, the acids is almost the same idea as an Arrhenius acid, except we are extending that definition. So Arrhenius specifically said ionize in water, whereas Bronsted-Lowry is saying that, that any chemical species, basically, any chemical that has an H to give away can be considered an acid. So HCl or HBr or CH3COOH, where this H is the one that's given away. All of these can donate their H's by, see this bond over here? So that's one electron from the hydrogen and one electron from the chlorine. This chlorine can take the electron from the hydrogen and give that hydrogen ion now proton, because it's lost its electron away. So it's donating the H plus by accepting that electron from hydrogen, and therefore it acts as an acid. Bases accept the proton from an acid. So for example, ammonia, that's right here, NH3. Bases usually have a negative charge or a lone pair. The negative charge comes because of a lone pair, so in general they should have a lone pair at on some atom. And when you see a proton that's coming, one of these electrons is kind of shared with this proton, after which a bond is formed. So this makes the bases accept H plus by kind of giving away this electron to the H plus so that the H can form a bond with that atom. So that's the new definition of an acid and base. Acids have an H to donate. Bases have a lone pair so that they can accept the H. You might ask why this H is not an acid. Technically, it could act as an acid, but the problem is the carbon bond here is not really amenable to accept that hydrogen. It doesn't really, accept the electron. So these hydrogens are kind of closely bonded to carbon. And that has to do with, again, electronegativity differences between the Cl and the H. And there's a couple of other factors that influence how easy it is to donate that H plus, so to speak. And that is in our strong acids versus weak acids theory, which will come later. But ammonia as a base has one lone pair, so it accepts an H plus. So this is the Bronsted-Lowry definition of an acid. And each acid has its conjugate base almost. And this is because let's look at the Cl. So once it has accepted the electron from the hydrogen and donated the hydrogen, it becomes a Cl minus, which then means that Cl minus has a lone pair to accept the hydrogen back. So any acid has its conjugate base. And the relation between the two is just the difference of one proton. It's important to note that it is a difference of a proton, so it's difference of one hydrogen atom and one positive charge. So HCl is going to give you Cl minus plus H plus, right? So the negative charge comes here because I have technically taken away this H plus. Same way over here, I've taken away the H plus, so the negative charge is present. These are the reverse, so this is a acid because it has an extra H to give away. It has 4 technically, and it gives away one of the H and now gets a lone pair free. So this ammonia acts as a base because it has a lone pair. So again, as soon as it gives its hydrogen away, it then gets a lone pair, which can then accept a hydrogen back, going back to the acid. So there's the interconversion between these two, and that's why they're a pair, like a conjugate base pair. Similarly, losing the hydrogen and obtaining the lone pair. One of the oxygen gets the lone pair. Again, it's important to note that I said losing hydrogen, but technically he's losing a proton. So this is minus plus, the proton goes away, and you're left with NO3 minus. All right, so this is the general equation. Your acid has the proton in it. The base has a lone pair, which then it uses to accept this proton from the hydrogen. So the base gets a positive charge, and the previous acid, the A, gets a negative charge because it's lost the proton with the positive charge. And A minus now acts as a base because it has a negative charge and a lone pair. This now acts as an acid because it has a hydrogen to give away. So, write equilibrium expressions for dissociation of ammonia in water. So ammonia, NH3 plus water, arrow, NH4 plus OH minus. So what's happening here is I'm going to write water as HOH instead of H2O because that kind of simplifies what's going on. And here, ammonia has a lone pair, so it's acting as a base. Water has a hydrogen over here, so it acts as an acid. The water gives away the hydrogen to form OH minus, its conjugate base. Ammonia accepts that hydrogen to form NH4 plus ammonium, its conjugate acid base. So water here is acting as an acid. Note that the fact that that NH4 is a conjugate acid and OH minus is a conjugate base. The word conjugate just really means that it's in the product side, or it's it's basically the relation of NH3, and it doesn't mean anything apart from that. So this is, for all intents and purposes, just an acid. OH minus is just a base. We just use the word conjugate to indicate that it's in the products of a acid-base reaction. So dissociation of acetic acid and water. So as the name implies, acetic acid is the acid. So here water is going to act as the base because water also has 2 lone pairs on the oxygen that could potentially accept another hydrogen. So this hydrogen from ammonia is going to be given away after it has lost its electron. So the proton is going to be given away. So what's left is CH3COO minus. The proton then comes to the water, which becomes H3O plus. Note that because I've given a positive charge away, I have a negative charge, so I've given the positive charge away, so I have a negative charge. I have taken a positive charge, accepted a proton, so my net charge is positive. So this would be the conjugate base. H3O plus would be a conjugate acid. So this just goes to show that water is amphoteric. It can act as an acid or a base. And for that matter, so can ammonia, right? So ammonia has, we know that it has a lone pair and can accept a hydrogen, but it also has 3 other hydrogens. So it can lose one of these hydrogens, thus becoming NH2 minus. This reaction doesn't really happen because it's very unfavorable. So ammonia does act as a base way more often than it acts as an acid. So that's the reason why. But technically, if it has H plus to give away, it could hypothetically act as a base. Or you could form that conjugate base of ammonia, at least. Okay, now what is a strong acid? Strong acids are acids that completely dissociate in water. What does that mean? So when I put HCl in water, it's like putting sodium chloride in water. I don't have any more HCl at all. I completely dissociate to give me H plus and Cl minus. This H plus is going to combine with water to become H3O plus. I'm going to use H plus and H3O plus interchangeably throughout this thing because they're H3O plus is basically H plus in water. So again, this reaction is going to go completely to the left, and if you look at its Ka value, or we'll talk about Kc value for now, it will be very much bigger than 1 because the reaction is so product favored. I'm just putting the Ka here just to show that if you're writing an acid dissociation equation, you should write Ka. So acid plus water. If you write any equation that has an acid plus water, you don't call it Kc anymore, you call it Ka, and that is H3O plus times Cl minus concentrations divided by HCl concentration. And there's almost no HCl concentration. So if you start with 0.1 moles of HCl, you get 0.1 moles of H3O plus and 0.1 moles of Cl minus, and that's complete dissociation. So HCl, HBr, Hi are all strong. HF is not strong, so that's an exception. Oxyacids, where the number of oxygens exceeds the number of hydrogens by 2 or more. So HNO3, HClO3, H2SO4, you can see that 1 to 3 is 2 difference, 2 difference, 2 difference. Nitric acid, we have nitric acid. I can't think of anything that I'm missing. Perchloric acid, technically HClO4, it's a 3 difference, so that's an acid. But yeah, that's how you identify a strong acid. Strong bases are all oxides and hydroxides of group 1 and 2 metals except beryllium. And you'll know a weak acid when you see one because it will usually be a nitrogen containing compound. Most weak acids have nitrogen in them. However, there are exceptions, and it's good to know this just for the future. Okay, acid plus base gives you salt plus water, and this is a double displacement reaction. Hopefully everybody's good with this. HCl plus magnesium hydroxide gives us magnesium chloride plus HOH, which is water. We have to multiply this by 2, this by 2, and we have a balanced equation. But yeah, that's basically when here, because there's an OH, we're not really talking about, we can think of this even in Arrhenius form, where the OH and the H combine to form water, and the Mg and the Cl combine to form magnesium chloride. Actually, we can't think of that in the Arrhenius form, scratch that. It's just a neutralization reaction. You don't have to think of it. Okay, hopefully everybody understands what a neutralization is. And now we will calculate the hydronium ions, and hydronium ions meaning H3O plus ions in the following. So these are pretty straightforward. We know HCl is a strong acid, so we'll write HCl plus water is going to give us H3O plus Cl minus. And this is a complete dissociation because it's a strong acid. So if I start with 0.5 molar, 45 molar HCl, I get 0.45 molar H3O plus. And that's the answer. So that was fairly easy. Same way, if I start with 0.45 molar H2SO4, I get 0.45 molar H3O plus. This might be a bit confusing because you'll see that I didn't take off the second hydrogen because for HSO4 minus to lose this hydrogen is very unfavorable because it already has a negative charge. So that's like stacking up another negative charge on it, which it doesn't really want to do. And so it will hang on to this hydrogen more tightly than it hung on to the first hydrogen. And so this losing its other hydrogen is not very favorable. This is technically a weak acid and not a strong acid. So we're only working with the strong acid, which is H2SO4, sulfuric acid, which donates one of its hydrogens to give to water so that water can become H3O plus, and this is the conjugate base of H2SO4. So here, part C is just a small dilution question. It says 40 mils of 0.75 molar diluted to 100 mils of, so we have to figure out our new concentration, which would, we can use C1V1 equals C2V2, which is our dilution equation. Basically, this says that the number of moles of acid doesn't change even after you add 100 milliliters or after you add 60 milliliters of water, but the concentration won't change, right? Because you're just adding water and diluting how much acid is there. So 0.75, which is C1 times 40 equals C2 times 100. So C2 just equals 0.75 times 40, divide both sides by 100, and we have C2 equals 0.3 molar. And so we know that our new concentration of HBr is 0.3 molar, so our new concentration of H3O plus will also be 0.3 molar because HBr is a strong acid. So here we have a neutralization reaction where you have an acid added to a base. Here we have to do a couple of calculations. We first have to find the number of moles of acid that we're reacting. So that was, we can do 0.175 moles per liter times 0.0358 liters, because we want units to be the same, times 0.0358, 6.265 times 10 to the power negative 3. Number of moles of base that I had was 70.8 milliliters times 0.0160, 1.133 times 10 to the power negative 3 moles. And so all my base is the limiting reagent because I have the least moles, and I'm doing this in I'm not doing this in a 1-to-1 ratio. Whoops. You have to be careful because the balanced chemical equation will be HNO3 plus MgOH2 gives us MgNO3 twice plus 2HOH. So there's to be a 2 here. And so we have to technically divide this by 2 to find our limiting reagent. Again, you can find your limiting reagent whichever way you want. but in the end, it's still going to be your base, which is your limiting reagent. Even though it's a 2-to-1 ratio, there's way more. There's 6 times as much acid as there's base, and we only need 2 times as much acid. So we can calculate